Hello and welcome back. Let's talk about lines and planes. Now, in 3D space, we can have many things. In linear algebra, using linear expressions, we can only really create lines and planes. So a line is something like a pencil, but an infinite pencil. Imagine it goes on and on everywhere. A plane is like this, say, but it goes on and on forever. Now, there's many ways to represent these, at least when we're talking about planes. Lines, there's only a few ways you can really show lines in terms of variables, of course. You can draw many lines. But let's talk about what we need to define a line. Well, let's say we have an origin here. And we've got a point that's on the line. We'll call that point P. Now, we know that that point is in our plane. But we know that in 3D space, this line could, just imagine it's still stuck on this point. It could rotate anywhere along this point. So we don't have a line quite yet defined. But if I define a vector that is what we call a direction vector, that is parallel to the plane, say something like this, or parallel to the line, sorry. Well, now we know that the line goes through this point and it has to be parallel to this vector. So our line is now fixed. Remember that this line is infinite. So this dotted line is our line, and this solid line with the arrow at the end, of course, is our vector. Now we will call this vector V. How we represent this parametrically would be that x, this is your x1, x2, x3, or maybe in vector calculus you're talking about x, y, z. This equals the point P, so a vector to the point P, right, plus V. Now this would just be giving us this point right here. But we want this point to go everywhere along here. So if we scale this vector by an arbitrary amount, t, well, now we have our infinite plane. Now, or infinite line, sorry, I'm always getting these mixed up. If we wanted our line to span from some certain amount, we would constrain t. But as of right now, we're just saying that t runs from negative infinity to positive infinity. Okay, so let's look at an example for a line. Let's say a line goes through a point 0, 1, 2. Okay, and it's parallel to a vector 1, 1, 1. Okay, how do we represent this line? Well, we know that it's P plus some scale of this vector. So we've got 0, 1, 2, plus our scale, T, times 1, 1, 1. Simple, right? Now, I will admit to you guys, I did, when we first learned about this in my course, I kind of struggled with the concepts of these 3D spaces, but practice makes perfect, right? So yeah, I mean, that's lines. Well, now we need to get into planes. We need to start talking about something a little more useful, I guess you could say. So I'm just going to keep this up. We've got our point, we've got our vector pointing to the point, we've got our vector parallel to this line. Well, what if I wanted to take a plane? Well, a plane is in 2D space. A line is in 1D space. So if we took another vector and said that this was also parallel to the plane, well, now we've got a 2D space spanning kind of like this. So this is all our plane here. And that's not really a great representation, but let's say our origin was right here, and I have a vector that, keeps this stuck right here. And then we take two vectors, okay, parallel here, and then maybe it's parallel here, okay? Well, now we need to make this plane parallel to both of these lines. There we go. Now this plane is stuck. We can rotate it like this, but that's just going to be the same plane if it keeps going on and on forever. So that's planes, but we know what they look like. Let's try to represent it parametrically. Well, we can say we have our point P, like in the line. Let's add our TV, like in the line as well. But we also have one more vector. So we're going to scale this by S times this other vector, we'll call it U. And that's a plane. That's one way to represent a plane. So, like in the past example, let's look at another one. But for planes, we can ask you a few more questions. Let's say we have a plane that passes through the points 0, 1, 1, another point 1, 4, 5, and a third point 3, 7, 1. Okay. It's a bit of a strange bracket. Well, this doesn't look like this, right? So this is where things get confusing. But my problem-solving technique for finding the equation of a line or a plane, or specifically planes, because there's more questions we can ask ourselves, is just to sketch. So let's sketch out a plane. Let's sketch out a section of this plane, right? Because it's infinite. And we've got 3 points that are in this plane, so let's draw these 3 points. Let's call this point A, this point B, and this point C. Well, we know that this plane is constrained to these 3 points, so if I gave you 1 point, we could rotate the plane however we want. It's just going to be stuck to this point. If I give you 2 points, it can rotate, but it can't translate. And if I give you 3 points, that plane's stuck there. So we know that we have enough information. But how do we turn these into vectors? Well, let's think about what do we need? Well, we have a 1 point. We could choose any of these points. Let's say that our point, let's use the color red. Our point is this point right here. Let's use the color green for V. How can we find a V? Well, we can actually just do that. And we can find that vector simply. Let's call these points A, B, and C. I forgot to write that down. Okay, so this vector is just B minus A, because the change in the vector is going from the point B, or going from the point A to B, so B minus A is how far it traveled. Finally, we have our vector going from either B to C or A to C. Truth be told, they're the same thing. I hope my orange works. Yeah, okay. U. Let's call U this. Boom. So our P is A, 0, 1, 1. Our T is just a parameter. Our V is B minus A. So we've got 1 minus 0 is 1. 4 minus 1 is 3. 5 minus 1 is 4. And our U is this orange vector, C minus A, because it goes from A to C, so C minus A is the change. 3 minus 0 is 3. 7 minus 1 is 6, and 1 minus 1 is 0. Let's add in our parameters, T and S, and that's the parametric equation of this plane. Okay, so great. We've made a plane in a vector form just by knowing 3 points. But that's not all there is for planes. The last thing we have for planes is the normal equation. Now on this plane, there is a vector that is always at a right angle with every point on this plane. You know, you could go into the proof for this, but just trust me on this one. We'll call this vector n. And the normal equation for this plane, well, obviously we're going to want to incorporate the normal vector. So, let's choose some point. Let's ignore these vectors here now. Let's choose some point x on the plane. Well, this vector from x to p, or p to x, p to x, that one's going to be parallel with the plane because it's got the point and it's got the point x on the plane. Well, the normal is at a right angle to this vector because it's at a right angle to any point on the plane. So, well, what does this mean? Well, if something's at a right angle, we might remember from dot products. Let me just write this x in so we still have the equation of this same plane. The thing about it being at a right angle is that this vector, dot producted with this vector, is going to be 0. So the vector, which is x minus p, dot producted with n, is equal to 0. Okay, so n dot x minus n dot p, just distributing here, equals 0. So n dot x equals n dot p. Nice. Very nice. So how do we find the normal? Well, we're just going to work with this plane here. What type of a vector is normal? Well, remember with cross products that if you cross a vector with another vector, you get something that's normal to the plane. So let's call this vector v and this vector u. V cross u is n. And according to my calculations that I did before this video, we have that the n is negative 24, 12, minus 3. Now you might notice everything's times by 3. If I just scale this vector, divide it by 3, it's going to get a little shorter, but it's still going to be at a right angle. So our equations are still going to work because they were just derived that this was normal or at a right angle. So let's just call it negative 8 for negative 1. Okay, n dot x equals n dot p. Our x is just x1, x2, x3, right? Because this point has an x1, an x2, and an x3. So we've got n dot x is going to be negative 8x1 plus 4x2 minus x3, right? That's the dot product. And that equals our n dot p. Now, what point did we use here? Well, we can use any point that we were given. Now, I did erase the points, but I'll leave this to you guys. What you're going to get is 9, I believe. Nope, you're going to get minus 3, sorry. In my pre-worked example, I had divided by 3 already. Or I didn't before I went into this equation. But that's lines and planes. I mean, that's all you need to know about 3D space in linear algebra. So I hope this video helped, and thanks for watching. I hope to catch you in the next video.